Welcome to this first presentation about the best methods for alkylating amines. There are many ways to alkylate amines, and I've organized the most relevant methods into 5 presentations. In this first video, we discussed the alkylation with alkyl halides and related electrophiles. The remaining videos of this playlist will then deal with alkylations by aldehydes and ketones, by alcohols, by alkenes, and in the last presentation I'll show you some alternative strategies, such as the alkylation of sulfonamides or chloramines. The amines manufactured today on the largest scale are the 3-methylamines. These are prepared simultaneously in the gas phase from ammonia and methanol with the aid of solid catalysts. These acidic catalysts are not neutralized and deactivated by the produced amines because of the high reaction temperature. The resulting mixture of amines can also be equilibrated under these reaction conditions. Trimethylamine can, for instance, be converted into dimethylamine by treatment with ammonia. Methylamines are mostly used as synthetic intermediates for the preparation of the polar aprotic solvents DMF, DMA, and NMP. These excellent solvents are needed for the manufacture of polymers and electronic devices. Further applications of methylamines include the preparation of pesticides, detergents, surfactants, disinfectants, and the food and feed additive choline. A further important use of amines is as drugs. Here, the quantities are much lower than of solvents, but prices are higher. Most natural neurotransmitters are amines, such as histamine, dopamine, or serotonin. Because at physiological pH amines are almost completely protonated, the receptors for these amines have been optimized by evolution to selectively bind positively charged compounds. Therefore, most agonists or antagonists of neurotransmitters are also amines, such as, for example, the synthetic dopamine antagonist metoclopramide. Amines generally show good oral bioavailability, that is, a large fraction of orally administered amine will usually reach the bloodstream. Amines also have a high volume of distribution, what reduces their metabolic clearance and enhances their plasma half-life. The reason for this is that cell membranes are made of negatively charged phospholipids, and ammonium cations therefore diffuse well into tissue and stick to membrane surfaces. This lowers their plasma concentration and thus the fraction of amine flowing through the liver, where most metabolic degradation occurs. Plants figured this out long ago, and most plant poisons developed for protection against herbivores are therefore amines, such as strychnine, atropine, quinine, nicotine, morphine, and many more. One strategy to improve the pharmacokinetic properties of a neutral drug is therefore its conversion into an amine. Antibiotics have, for instance, been improved this way, one example being azithromycin. The alkylation of amines by alkyl halides and related electrophiles is a typical bimolecular nucleophilic substitution. The lone pair at nitrogen pushes electrons into the empty antibonding sigma star orbital of the carbon-halogen bond, thereby weakening it and forming the new carbon-nitrogen bond. Nucleophilic attack by nitrogen at the halogen atom occurs only when the halogen-bound carbon atom can form a well-stabilized carbanion and thus act as leaving group. Polyhaloalkanes and haloketones sometimes react this way. The most common side reaction is beta-elimination of the hydrogen halide to yield an alkene. Tertiary amines can also be quaternized if an excess of electrophile is used, and with allylic halides, allylic inversion can occur. Unfortunately, many examples of low-yielding amine alkylations have been reported. The main reasons for these low yields are that the reactions were too dilute or that only one equivalent of alkylating reagent was used. As the alkylation proceeds, the concentration of both starting materials will of course drop further and may reach a level where the alkylation can no longer go to completion. Then, alkyl chlorides are quite unreactive and not well suited for the alkylation of amines. Thus, to achieve high yields of alkylated amine, the reaction should be run neat or in the presence of only small amounts of some polar solvent. One of both reacting partners should be used in excess, and ideally alkyl bromides should be used as electrophiles. Industrial scale quaternizations are often conducted with methyl chloride under pressure. If an alkylation requires strong heating, it is a good idea to use alkyl halides which cannot undergo beta elimination, such as methyl, allyl or benzyl halides. Here's a typical example of a low-yielding amine alkylation, but many more have been reported. The equimolar ratio of reactants and the unreactive alkyl chloride were probably the main reasons for the low yield. Not even the addition of an excess of sodium iodide helped in this case. A similar reaction with an excess of alkyl bromide gave a much better result already at room temperature and higher dilution. This is a further example to show how the replacement of an unreactive alkyl chloride by an alkyl bromide can enhance the yield of amine alkylations. Here, triethylamine was quaternized with octyl chloride and octyl bromide in refluxing acetonitrile. Only the bromide gave an acceptable yield of ammonium salt after 2 days. Alternatively, the reaction with octyl chloride may have succeeded if conducted at higher temperature in an autoclave. The nucleophilicity of amines, which is a kinetic property, depends on their basicity and steric accessibility. For small electrophiles and sterically undemanding amines, there is often a good correlation between nucleophilicity and basicity. But if the electrophile or the amine becomes sterically crowded, then the rate of alkylations will drop sharply, even if the amine is strongly basic. Here, the rate of amine methylations by methyl iodide in methanol is shown for ammonia and 3 primary, secondary and tertiary amines. All 3 primary amines were alkylated about 10 times faster than ammonia, because the alkyl groups enhance the nucleophilicity and basicity of nitrogen more than hydrogen does. This is the reason why primary amines are difficult to prepare from ammonia and alkyl halides. The initially formed primary amine will be alkylated faster than ammonia, and mixtures of primary and secondary amines result. Secondary amines are also alkylated faster than primary amines, but for tertiary amines the steric effect becomes dominant and quaternizations proceed slightly more slowly than the alkylation of secondary amines. The hydroxyethyl group is electron withdrawing, what causes the nucleophilicity and basicity of ethanol amines to be lower than that of simple alkyl amines. A comparison of reaction rates with basicities shows that there is some correlation, but not a perfect one. Diethanolamine, for instance, is less basic than ammonia, but about 10 times more nucleophilic toward methyl iodide. Then, some bicyclic amines, such as quinoclidine or DAPCO, are far more nucleophilic than ordinary amines, although their basicity is similar to that of alkyl amines. Therefore, basicity alone cannot be used to predict the alkylation rate of a given amine. Carbon-nitrogen single bonds are significantly shorter than carbon-carbon single bonds, and amines with bulky substituents are therefore highly strained and difficult to alkylate, in particular with sterically demanding electrophiles. For instance, diisopropylamine can be ethylated with diethyl sulfate in high yield by refluxing a neat mixture of the reactants. The isopropylation of diisopropylamine, however, is much more difficult. Under optimized conditions, a yield of only 29% could be attained by heating a neat mixture of the amine with an isopropyl sulfonate for 60 hours. Terzbutyl isopropylamine could no longer be isopropylated, and elimination to yield propene was probably the main reaction pathway. Even diethylamine is difficult to isopropylate, as shown here. Solvent-free conditions gave only 30% yield, but addition of a small amount of glycerol and heating for 3 days increased the yield to 60%. This table compares the rate of quaternization of quinoclidine by various alkyl halides in chloroform. The rate of the chloride was set to 1 for each alkyl group. This comparison shows that fluorides are completely unreactive and that bromides react 40 to 80 times faster than chlorides. Iodides are only about 2 to 3 times as reactive as bromides. Therefore, if a given alkyl chloride is too unreactive, the corresponding bromide will be a better choice, while the iodide will only be marginally more reactive than the bromide and not really worth its high price. Because of the high basicity, amines can also bring about beta elimination, in particular sterically demanding amines. Diisopropylethylamine, for instance, is particularly well suited for dehydrohalogenations. This table shows the ratio of alkylation to elimination for the reaction of piperidine with various alkyl bromides in petroleum ether. This is a poor solvent which slows down almost any type of reaction, hence the low reaction rates. With ethyl and propyl bromide, less than 1% of elimination occurred. Isopropyl bromide, however, reacted more slowly than the primary bromides and gave about 3% of propene. When the reaction temperature was increased from 90 degrees Celsius to 130 degrees Celsius, the extent of elimination increased to 8%. Finally, cyclohexyl bromide underwent almost complete elimination and yielded only 15% of cyclohexyl piperidine. This facile halide elimination from cyclohexyl halides has been observed on numerous occasions and is caused by the steric shielding of the antibonding carbon-halogen orbital by the cyclohexane ring. This here is an example of the alkylation of ammonia with a simple alkyl chloride. Despite the fourfold excess of ammonia, mostly a secondary amine was obtained because octylamine is approximately 10 times more nucleophilic than ammonia. Also substantial amounts of the tertiary amine were formed. If the electrophile contains electron withdrawing groups directly attached to the halogen-bearing carbon, then the amine resulting from reaction with ammonia will be less basic and less nucleophilic than normal alkylamines, and the tendency to act as nucleophile to yield secondary amines will be diminished. It is therefore possible to prepare alpha amino acids by treatment of alpha bromo acids with an excess of ammonia, as shown here. It is not always easy to predict if a given alkyl halide will undergo elimination or amination upon reaction with an amine. Alpha-halocarboxylic esters and lactones usually yield tertiary amines when treated with secondary amines, as in these examples. In the third example, however, triethylamine caused mostly beta elimination of hydrogen bromide from alpha-bromo-butyrolactone, despite the fact that diethylamine and triethylamine are both methylated by methyl iodide at similar rates. This here is a further example of the alkylation of a secondary amine with an electrophilic carboxylic acid derivative, a lactam mesylate in this case. Despite the use of dipea as auxiliary base, no elimination, but mainly the expected alkylation with clean inversion of configuration occurred. Not only ammonia, but also primary alkylamines are difficult to alkylate only once with simple alkyl halides. Only halides with electron withdrawing groups, such as alpha-halo esters or nitriles, will convert primary amines cleanly into secondary amines. Simple alkyl halides, however, will usually yield mixtures of secondary and tertiary amines. Interestingly, it has been found that cesium salts can increase the ratio of monoalkylation to dialkylation of primary amines, as shown here. In this example, the addition of one equivalent of cesium carbonate enhanced the yield of monoalkylated amine to 81% from 47% when no additive was used. In the second example, cesium carbonate did no longer work, but instead the selectivity could be enhanced by addition of cesium hydroxide. Thus, these reactions will probably have to be carefully optimized for each pair of reactants. This is an optimized example of the alkylation of a primary beta-iryloxyethylamine with a substituted 2-chloroethanol. The product was formed in high yield when a twofold excess of amine was used, also because the product was a very unreactive amine of low basicity, similar to diethanolamine. Mixtures of DMSO and even DMF with strong bases can decompose violently, and it remains to be seen if this procedure can be scaled up safely. The example on the next slide is much safer and better suited for large-scale preparations. This example is similar to the previous one. Instead of an alkyl chloride, a bromide was used as electrophile, and the nucleophile was a substituted terzbutylamine. Here, no DMSO but butyl acetate was the solvent of choice, and only a slight excess of bromide was sufficient to achieve a high yield of secondary amine. The product was both sterically and electronically deactivated, what prevented the formation of a tertiary amine. Interestingly, the starting materials also contained a rather reactive sulfonamide and an unprotected phenol, which could also have been alkylated under these conditions. This was, however, not observed. Amines can usually not be alkylated under acidic conditions because ammonium salts are not nucleophilic at all. There are, however, examples of the alkylation of amines with electrophiles that require some slight activation by acids. This is, for instance, the case for oxazolines, which are formed upon treatment of two haloethylamines with bases. Such oxazolines can be used to alkylate amines, but catalytic amounts of an acid are required, as shown here. The reaction mixture was still basic because of the excess of amine, but the ammonium tosylate was capable of activating the oxazolines sufficiently for the alkylation to proceed. A similar effect is seen when two halopyridines are used as electrophiles for the arylation of amines. These arylations work best with a small amount of acidic catalyst. Anilines are much less basic and nucleophilic than aliphatic amines. Still, the same problem of single and twofold alkylation as with primary aliphatic amines occurs, as shown here. In this case, the selectivity of the alkylation could be increased by addition of a zeolite. Neopentyl-derived electrophiles are exceedingly unreactive, also toward amines. Even the addition of a strong base, such as an iminophosphorane in this case, did not help to bring about neopentylation of a primary amine. In this example, the authors found that a radical nucleophilic substitution could be triggered with light and a copper catalyst. Diarylamines and nitroanilines are usually too unreactive to be alkylated directly by alkyl halides. Such amines are, however, often quite acidic, and the nucleophilicity can be increased by deprotonation. The example on this slide is a phase transfer catalyzed synthesis of the antipsychotic drug chlorpromazine. Although only a slight excess of an unreactive alkyl chloride was used as electrophile, a high yield of the target product was obtained. In this example, instead of a free diarylamine, an acetamide was used as a starting material, and an alkyl bromide as electrophile. Despite the base sensitivity of the product, only about 10% of byproducts resulted when the alkylation was conducted in acetone as solvent and with solid potassium hydroxide as base. In THF, however, extensive elimination of chloride occurred. This example is similar to the previous one. Again, an excess of bromochloropropane was used as electrophile, but here a weaker base and a phase transfer catalyst provided for a clean alkylation of the diarylamine. The resulting alkyl chloride was treated with an excess of hydroxyethylpiperacin and a high yield of the tertiary amine. The antidepressant drug opipramole was obtained. So, what are the potential side reactions? As already shown in some of the examples, one important side reaction is the formation of alkenes by elimination of hydrogen halide. Under strongly basic reaction conditions, some alkyl halides without beta hydrogen may even undergo alpha elimination and yield an intermediate carbene. This can, for instance, occur when attempting to alkylate deprotonated aliphatic amines, which are extremely basic. If anilines are to be alkylated in the presence of catalytic amounts of acids, alkylation at the arene is a typical side reaction. A further potential side reaction is the reduction of the alkyl halide to an alkane. Halides with a halogen-bearing carbon atom can form a well-stabilized carbanion may act as electrophilic halogenating reagents and not as carbon electrophiles. This is often observed with polyhaloalkanes, but can also occur with alpha-haloketones and related compounds. In this example, the starting bromoketone was rather unreactive, but could be partially debrominated by heating with dimethylanilene. With triethylamine, however, no reduction occurred. Here's a short selection of some further examples, but many more have been reported. The next presentation is about the use of aldehydes and ketones as alkylating reagents. These are often more selective than alkyl halides and do not quaternize tertiary amines. See you then.